We have successfully calculated a probability, but we are still left with defining what it is, right?
Yes, I'm ready.
Let's use something simple like these dice to lay out the framework of probability. Imagine rolling this die again and again and again. That's an experiment. Each roll of this die is one trial, and each trial has an outcome. In this case, there are 6 possible outcomes on a die roll. The die is assumed to be fair, so these outcomes are equally likely. Individual outcomes may not be of interest to us. We may want to examine a set of these outcomes. That's what we call an event. For instance, think of the event where the outcomes are even, that is 2, 4 and 6. The collection of all outcomes is what we call sample space. Lisa, what's the sample space in our case?
All outcomes? That's 1, 2, 3, 4, 5, 6?
Correct. We are ready to quantify our ideas of probability. We just talked about the event that the outcome of a die roll is even. What we wish to do is to place a meaningful number on the event by asking, what's the probability of this event? This is our first time, so I'll go about all of this exhaustively. Our sample space is given by the set S, which is 1, 2, 3, 4, 5, 6. An even outcome is summarized by an event, which is simply the set 2, 4, 6. Intuitively speaking, the probability of an even outcome has a chance of 3 in 6 or 1 in 2 or 50%.
Of course, a die roll can equally be odd or even.
You know enough about sets, so a diagram will make all of this easy to understand. The sample space S is the external shape. Inside it is an event E, which is any subset of our sample space. We are ready to define probability for this event. It's written as P of E and is simply the size of E over the size of S. Let's get some practice. The largest subset of S is itself. We call that a certain event. Lisa, what will be its probability?
The size of S divided by the size of S? That's 1.
Yes. What's the smallest an event E can get? We all know about the null set which contains nothing. You can guess that the probability is just 0. We just don't stumble upon null sets directly. For instance, while it's nice to imagine persons 18 and under making over $50,000, there's no one in our training set. So the probability of this event is 0. Now the complement of an event E is the set of outcomes in the sample space that don't belong to E. It's written as E with a C on the top. Lisa, what do you think of the event E complement in our example?
Let me think. The outcome of a die roll must not be even. That's the set 1, 3 and 5.
Right. And its probability is again a half. If the dark brown portion accounts for the probability P of E, then the light brown one should have 1 minus P of E, right? We have a law. P of E complement is 1 minus P of E. This result looks deceptively simple, but it can be used to great advantage to solve problems. There are several occasions when figuring out the complement of an event is the better way out.
Like a glass being half full?
You're a real philosopher, aren't you? The real tricky part is when we have to apply it to problems in the real world, such as the questions we have with our census data. For that, we must first map all of our terms into the context of the problem. Let's begin with the outcomes. What are they, Lisa?
Each row in our data set?
That's right. We could regard the census as an experiment that was conducted over people in the US, and each line on our spreadsheet captures one outcome. We then specified an event. What was that, Lisa?
The event that a person selected at random from this set makes over $50,000.
Yes, Let's call that event E. We then look up our pivot table to figure out how many of these outcomes are in favor of E. And that is 7,507. We got the numerator in the probability expression. Most people do well on this front. It's equally important for them to identify the correct sample space. And to decide what it is in our question, we must examine the statement carefully. We asked, which set did we select that person at random from?
The entire spreadsheet, of course.
Right. And that makes for 30,160 rows or persons which go into the denominator. Let's bring it all together now. The probability that a person who is randomly chosen from this data set makes over $50,000 is given by 7,507 divided by 30,160, which is 0.249. Or when there's no one looking, we'll round this up to 0.25. Let's stop for a moment to talk about how we must present our conclusions. Business folks do not like to split hairs between quantities like 0.249 and 0.25. They'll appreciate you even more if you stated that 1 in 4 persons within the data set made over $50,000.
That's much more palatable.
She's got an appetite for numbers, you know.